Lava is hot enough to melt steel and most other metals immediately. Normally, only Mother Nature can stop lava from flowing, and not without putting up a fight first. You'd think pouring water on it would be a good idea, but you'd simply get steam and a glassy crust at best. What have I told you?
This Pokemon blasts cryogenic air out from its mouth, which can instantly freeze lava.
It seems impossible. No animal or even machine can do something remotely similar. So, could Baxcalibur's breath exist in real life? To answer this, we must turn the Pokemon trait into a clear physics problem. Essentially, at what temperature and heat removal rate would an exhaled breath solidify lava? Concretely, if Baxcalibur blows a certain volume of cryogenic air, we'll see what this means in a moment, onto lava, can that air extract enough heat fast enough to cool the rock from its melting point, which is the melting point of the majority of the composition of lava, down to the freezing point? We will estimate the required power and heat flux for such a breath, then compare them to reality. We will test two interpretations of the Pokédex, since none of its writers made it unambiguous. I mean, what do you expect from a biology teacher? First, Baxcalibur can solidify 1 liter of basaltic lava, a small bucketful, in about 1 second, which would practically look instant to the average observer. Alternatively, Baxcalibur can solidify only a thin crust rapidly enough to look like freezing. We need to consider 3 laws of nature before deciding whether Baxcalibur's breath could exist. First, lava stores an incredible amount of heat. Cooling lava isn't just as simple as lowering its temperature. 2 separate energy bills must be paid. The first is sensible heat, the energy required to change the temperature of the rock. The second is latent heat, the energy stored in its bonds to change its state of matter. Volcanology measurements tell us that basaltic lava at around 1200 degrees Celsius has a density of about 2600 kilograms per cubic meter, a specific heat capacity around 1450 joules per kilogram per degree, and a heat of fusion, how much energy its atomic bonds need to absorb to go from liquid to solid, of roughly 500 kilojoules per kilogram. In other words, even a cup of lava is a staggering reservoir of thermal energy. Secondly, that heat cannot simply vanish. You can add heat to an object, you cannot add cold to an object. The rules of thermodynamics state that heat flows from a hot object to a colder one. Always. Even freezers have to obey thermodynamics, which is why the back of a fridge or freezer is literally a radiator. If Baxcalibur freezes lava, that heat must end up in one of 3 places: the expelled breath, the ambient air, or Baxcalibur itself. Thirdly, you could have air close to absolute zero, but it would be practically useless. That's because air is a terrible cooling medium, unless you force it to move extremely fast. The real bottleneck is rarely how cold the air is. The bottleneck is how quickly heat can cross the thin boundary layer between the object you're trying to cool and the airflow. Engineers measure this using something called a heat transfer coefficient. Even in aggressive industrial cooling, like the air jets used to protect turbine blades, you typically see values around 1000 to 30,000 watts per square meter per degree, corresponding to a heat flux or flow of energy per unit area per unit time on the order of a megawatt per square meter in extreme environments. Could a mouth-sized blast of air ever remove heat fast enough to keep up with the enormous energy stored in molten lava? Let's tackle this question. The rate at which Baxcalibur's breath can extract heat from lava through a given area, in this case the size of its mouth, is known as its heat flux. If we assume the lava mentioned in the Pokédex is basaltic lava, which starts at 1200 degrees Celsius, and we cool it to 800 degrees Celsius to be completely solid, rock solid, that's a temperature drop of 400 Kelvin. From the volcanology measurements from earlier, we know that for basaltic lava, the total energy to turn 1 kilogram of lava to solid basalt is 1.08 megajoules per kilogram. Now take 1 liter of lava with a density of around 2,600 kilograms per meter cubed. 1 liter or 0.001 meters cubed has a mass of around 2.6 kilograms. That means the energy to solidify 1 liter is approximately 2.8 megajoules. If instantly means about 1 second, Baxcalibur needs a cooling power of roughly 2.8 megawatts. That is megawatt territory, the scale of a small wind turbine delivered as a breath. That probably explains why the move is icy wind and not icy breath. The best air jets used to cool turbine blades have a heat flux of around 1 megawatt per meter squared. A large animal's open mouth might have a jet interaction area of approximately 0.01 meters squared, with an approximately circular mouth bearing a diameter of around 11 centimeters across. At 1 megawatt per meter squared, a 0.01 meters squared footprint transfers about 10 kilowatts. In 1 second, that removes 10 kilojoules. But our lava needs 2,800 kilojoules for 1 liter. So, under optimistic heat flux assumptions, a mouth-sized cold air jet is short by a factor of roughly 280 times. Do you see the problem now? The problem isn't getting cold. The problem is moving heat fast enough through a tiny mouth-sized area. This is why it is perhaps more plausible that the Pokédex might be describing something more superficial. Literally. According to the US Geological Survey, the outer surface of erupting lava can cool by hundreds of degrees per second when first exposed to air. Crucially, that doesn't mean the whole flow freezes. It only means a thin crust forms while the inside remains molten. So Baxcalibur could potentially freeze lava in the visual sense by rapidly thickening the crust, turning a glossy molten surface into a solid shell that looked like frozen rock. If you've been paying attention, you would have realized that the air from Baxcalibur's mouth and lungs would have to come in contact with much more than just the lava it wants to freeze. If Baxcalibur really exhales cryogenic air, then the surrounding air would start to not behave like its usual gaseous self. At normal atmospheric pressure, oxygen boils at around 90 Kelvin or minus 183 degrees Celsius, while nitrogen boils at around 77 Kelvin or minus 196 degrees Celsius. So, if Baxcalibur's breath were anywhere near liquid nitrogen cold, the surrounding air wouldn't just chill. It would start condensing into liquids. You would expect to see liquid oxygen and nitrogen droplets and dense clouds of fog and ice as atmospheric water vapor freezes instantly. Let's assume the more plausible version is the intended one. Baxcalibur can rapidly crust and immobilize the surface of lava, not instantly solidified by the bucketfuls. Even then, it needs two things biology doesn't offer in one package: a way to generate cryogenic airflow quickly, and a way to avoid freezing its own throat while doing it. How do fridges and freezers work? It is based on a simple thermodynamic trick. If you expand compressed gas rapidly, its temperature drops. NASA's educational resources describe the basic pressure-temperature relationship for this kind of process. For air, the relevant thermodynamic constant, called gamma, is about 1.4, which means the temperature after expansion depends strongly on how much the pressure drops. In plain English, if Baxcalibur stores air at extremely high pressure and then releases it suddenly, the expanding jet could become extremely cold. Cold enough in principle to approach cryogenic temperatures. But there is a catch. To drop from something like body temperature, which is around 300 Kelvin, down to around 90 Kelvin, the point where oxygen begins to condense, you would need pressure ratios on the order of tens of atmospheric pressure. That means Baxcalibur would effectively need to store air at dozens of atmospheres. An atmosphere is the unit of the pressure of the atmosphere at sea level, or about 101 kilopascals. Let's not get carried away with units. This introduces a very different problem. Biologically, Baxcalibur would require a pressure vessel in its torso comparable to a scuba tank, a compressor-like organ constantly recharging that tank by burning huge amounts of metabolic energy, and valves and nozzles that can survive enormous pressure swings without rupturing, icing shut, or melting when pointed at lava. Surprisingly, none of that violates physics, but it does mean Baxcalibur would be something like a living cryogenic machine. Just now when I said, or melting when pointed at lava, that's because another problem arises when you point a cold stream at a massively radiative object. In this case, the lava convects heat back toward the source of the cooler region. As a result, in addition to the working heat pump inside Baxcalibur's body, Baxcalibur will need to have thick insulating tissues around its airways, some kind of superficial self-healing icy mucosa, and a tapering airway that ensures the coldest expansion happens furthest away from its internal organs. Incidentally, elite human athletes such as sprint cyclists can briefly produce mechanical power in the 2.4 to 2.5 kilowatt range. For a 210 kilogram creature, tens of kilowatts for brief bursts is absolutely credible. But the megawatt scale to instantly freeze a liter of lava is clearly in a totally different league. Since the outer surface of fresh lava cools incredibly quickly when exposed to air, Baxcalibur doesn't need to perform miracles to create a frozen lava look. It only needs to accelerate what nature already does at the boundary. Inside modern jet engines, turbine blades sit in gas streams approaching 1400 degrees Celsius, hotter than many lava flows. If those blades weren't cooled aggressively, they would melt in seconds. One of the most effective techniques for maintaining these blades while in flight is with impinging jet cooling. Pressurized air from the compressor is blasted directly onto the metal surfaces that need protection. The air would be around 600 degrees Celsius, which is cooler than the surrounding gas, so it carries heat away. Of course, carbon-based life forms don't tend to have precisely engineered nozzles, materials, and geometries. You might have wondered whether Baxcalibur would have been better off being a water type. During the 1973 Outfell eruption, firemen pumped seawater directly onto advancing lava. How much water do you think they used to stop the lava from reaching the Icelandic city? According to a report filed in the US Geological Survey, pumping rates reached up to 1,000 liters per second at times, and a total of about 6 billion liters of seawater were used by the end of operations. The same report estimates that this converted on the order of 4 billion liters or 10 billion kilograms of molten lava into solid rock. Solid rock. That is the scale required when the objective is to freeze lava, because water has a vastly higher specific heat capacity than air, and the change of state from liquid to gas also soaks up a lot of energy. If Baxcalibur truly existed, its cryogenic breath would change the world. In the best case scenario, it could become an extraordinary disaster response tool. Rapidly thickening the crust of advancing lava flows might buy precious time for evacuation interventions. But the same power would also be extremely dangerous. Sudden cryogenic blasts could cause thermal shock, snapping pipes, shattering windows, and fracturing rock. Even infrastructure designed for cold climates isn't built to survive instant drops of hundreds of degrees. A single uncontrolled burst could leave behind fields of brittle glassy rock and shattered structures. And then there are the geopolitical implications. A creature capable of freezing machinery, infrastructure, or vehicles in seconds would inevitably attract military interest. A blast that can solidify lava could just as easily immobilize engines, crack armor, or disable electronics through thermal shock. Of course, the physics we've explored suggests this ability would be incredibly expensive biologically. A creature performing megawatt-scale cooling would need enormous metabolic input and would likely reserve such attacks for rare high-stakes situations, which means Baxcalibur wouldn't be casually freezing landscapes every day. But when it did breathe, the results would be spectacular, terrifying, and impossible to ignore. If we take the Pokédex to mean Baxcalibur is capable of freezing large volumes of lava instantly, the answer is simple. It can't happen. Freezing just a liter of lava in a second already requires megawatts of cooling power, and the heat simply cannot move through a mouth-sized jet that quickly. But if Baxcalibur is only rapidly crusting the surface, making the lava look like it froze instantly, then the idea becomes much more plausible. At that point, Baxcalibur starts to look less like a purely fictional being and more like a highly engineered cryogenic machine, storing high-pressure air, cooling it with heat pump cycles, and protecting its body with extreme insulation. So, Baxcalibur lacks the caliber to be the ultimate walking cryogenic machine. From Baxcalibur's name, you would think it is supposed to be some kind of sword. Well, that probably is because the sword Pokémon already exists.